All right. Now, we're going to do a little advanced projectile motion here. All right, so for advanced projectile motion, I don't have a word problem written out. I basically just have a pseudo real-life scenario here that we're going to work through. So, tennis. I love tennis. Remember this one time back in tennis camp? By that I mean my actual gym class, and I like crushed this ball during gym class, and the teacher's like, "Oh my God, can you do that every time?" And I said, like, 1 out of 10. And then she like walked away as if I didn't exist. And I was like, well, that's kind of harsh. Okay, but in tennis, you serve the ball pretty much as fast as you can. And if I draw myself a little tennis racket here, all right, it comes down, and you want to like crush this ball, all right? And so there are some constraints though, and that is that when you hit the ball, you have to try and keep it in the court. And you also have to try and get it to go over a net. Now, the net happens to be 11.88 meters away from one of the end lines where the server hits the ball. And the net itself is 1.07 meters tall. All right, so that's the height of the net. And let's say this is like me serving. All right, let's say this is me serving. So let's say this is hit from a height of about 10 feet. So let's just say it's 3 meters high. And when you hit this tennis ball, you basically try and hit it down. You don't actually want to hit it forward or up. You want to try and hit it down so that you have kind of this arc that's going to just barely clear that net, and then it's going to land inbounds and therefore smoke the other person. You're like, yeah. All right, so let's say I was some sort of awesome tennis player, or let's just make this an awesome tennis player who looks weird. And let's say they can hit it with a speed of 100 miles per hour. Well, 100 miles an hour is approximately equal to 44 meters per second. All right? All right, so you're smashing this at like 44 meters per second, which is blisteringly fast, and you want to get that downward angle. So let's just assume that the downward angle is, let's go with 10 degrees here, 10 degrees. So you're firing this at a 10-degree angle below the horizontal because you want to hit it down. So we want to try and figure out, okay, where's this gonna fall? Okay, so where will the ball land? Okay, maybe you want to know, is it going to be inbounds, out of bounds? What's going to happen? Well, to solve this type of problem, you actually have to make a few steps. So this is actually a multiple step problem. So the first step is you have to ask yourself a question. Does it hit the net? Because I don't know if it's going to stay in bounds. I don't even know if it's going to hit the net. Okay, that's like the first thing you got to answer. Now, when you're going to answer this, you then have to basically say, okay, well, what am I going to use as my givens then? All right, now here's how I approach this. I say, well, okay, I'm going to do the same thing I always do, and I'm going to break my x's up from my y's. So in the x-plane, I know that my velocity in the x is going to be equal to 44 cosine of 10 degrees. All right. I know that. Then here's what I'm going to do. I'm going to choose to make this 11.88 as a known variable. So let's assume it goes this far. And what I'm trying to solve for now is I'm trying to ask, how high is it? So when it goes that distance, where is the ball vertically? Because if I check and the ball is above 1.07 meters, then it's going to go over the net. If it's below 1.07 meters, then it's going to hit the net. And if it's way below, maybe it hits the ground before it even hits the net, but we can cross that line a little later. So Now I'm going to say, well, to solve for this, I need to know my time of flight. Hey, look, it presents itself pretty nicely. And if I look at my y-plane, I know that my acceleration is that good old negative 9.8. I know that my velocity initial in the y-plane is going to be negative because it's a downward component, 44 sine of 10 degrees. And then I do not know the time, and I do not know this vertical component. So all unknowns. So now I can start solving. Now I've broken up all my information. So again, this x information is pretty readily available here. So I'm just going to use my equation for average velocity in the x-plane, because that's what it's doing. So delta x over delta t, substituting what I know. So 44 cosine of 10 degrees equals 11.88 divided by delta t. Delta t equals 0.274 seconds. All right, so that's one thing we've got to know. So that's going to be how long it's going to take this ball to go from the tennis racket to where this net is. So now I'm going to figure out, well, how high is it going to be? So that's going to be me analyzing the y-plane. And the equation that we're going to be using is delta y equals v sub naught delta t plus 1/2 a delta t squared. And so now I'm going to substitute in everything I know, and I actually have to expand this delta y first. So that's actually going to be my final minus my initial. Okay, so my final is actually where I'm going to be minus my initial. Well, I hit it from a height of 3 meters. So now my initial velocity is going to be that negative 44 sine of 10 degrees times delta t, which I know, so I should just put it in there now. Why wait till later? So I know that my time is 0.274 plus 1/2, negative 9.8, because that's my acceleration, times that time squared. So now all I have to do is solve for this y, because that's going to be how high it actually is. And if I crunch all those numbers, I figure out that the height is actually 0.536 meters. So unfortunately, if we are this powerful and we hit it with a downwards angle of 10 degrees, it's not even going to cross the net. Okay, it's going to go right into the net. It's only half a meter off the ground at the location where the net is, so it's not going to even cross the net. Sad, sad pandas. All right, so what do? Well, we're like, okay, hit it at a different angle. So I'm going to approach this again, but now I'm going to do it with a 7-degree angle. All right, so I'm going to fast forward, so you don't have to see all the different work, but you'll see, as I say, a 7-degree angle. We'll see where we can take it from here. 1 and... Okay, there. All right, so magically appeared. I don't know how that happened. Science is cool. All right, so now we notice we have a y of 1.18, which is bigger than the 1.07, I was right in my brain, that we need to get. So this will clear the nets. That doesn't tell me where it lands, though, so I have to do more math. All right, so here's what I got to change. In order to figure out where it lands, now I have to go and I have to figure out, will it actually land in bounds? So now I'm going to say, okay, where's it going to be if I were to take the entire length of the court? So to do that, I'm going to change my delta x. So now I'm going to say, all right, so I'm going to do this exact same problem, except my delta x is no longer 118. My delta x is now the entire length of the court, which is 23.77 meters. All right, so that's what I'm going to change in here. So I'm going to go back, I'm going to change in all these problems here. And so if I redo this, I get 44 cosine of 7, 23.77 delta t. So now the time that's going to take to hit the ground, 0.544 seconds. And so now I'm going to take that time and put that over here into my delta y equation. Why am I writing that equation? You already have it way up there. Let's just go straight to the numbers. It's supposed to be an eraser. It's supposed to be an eraser. Come on, you can do this. Erase, erase. There we go. Yay, technology. All right, so come on. All right, there we go. I'm not redoing this. I am not quitting now. And it's determined to stay here. So I guess I'm living with the scribble. So we got this. Now it disappears. Oh, come on, world. Okay, we can do this. I've been doing a few of these today, so I'm sorry if I'm getting a little punchy. All right, so we got y minus 3 equals. All right, now we're rocking and rolling. Okay, 44 sine 7 times our new time of 0.544 plus negative 9.8, 0.544 squared. So if we solve for this, we're going to get value of negative 1.3, let's say 7. All right. So what does this mean? Well, this means that it definitely landed inside the court, because if I did like a quick little sketch here, here's my court, here's the net. By the time it reaches the end, it is underground. Okay, so it must have hit somewhere inside. So, maybe your question is, will it land in bounds? Well, the answer is yes, it will land in bounds. We know that it's going to land in bounds. We know the fact it's going to cross the net. We also know it's going to land in bounds. I don't exactly know where it's going to land the x-plane, though. Oh, darn. Well, have no fear. If you really want to answer that question, then you can just repeat the procedure, except you're going to say, hey, if my vertical displacement, or my position, I should say, right here, is y equals 0, well, then what time is it going to be at y equals 0? All right, so look, I can do this problem in even a different way. I bet you didn't see this coming. You did not see this coming. All right, so I'm going to do this problem again. That's right. I'm going to do it even more because I love this problem. Not really. I'm just trapped in limbo. So if I want to solve with this knowledge of, hey, y equals 0, then I'm actually going to flip this. And if I look at my givens, now I'm going to do some changes here. So my x's and my y's, well, the velocities still stay the same. So I got 44 cosine of 7. I do not know my displacement now. Okay, I don't know that at all. But in the y-plane, I actually now know more information. So negative 44 sine 7.8. And now I know that my displacement in the y is going to equal 0. That's a lie. My final position in the y is going to equal 0. So my displacement in the y is going to be negative 3 because I fell down 3. So now we can punch into our equation. We know a lot of information about the y, so we can solve for time, take time over to here. So that's what we're going to do first. All right, so I'm just going to write that out, and then we'll have some magic of technology. So here's my setup, but you'll notice I have a quadratic, and I have to solve it with the quadratic equation. So I highly recommend that you find a way that works for you to solve quadratic equations, either a solver or a program or graph it or whatever, but you got to figure out a way to solve it. So I'm going to go solve it, and let's see what I get. Negative 0.407. Sorry, not negative, just 0.407 seconds as one of my times. But since it's a quadratic, you're going to get 2 times. The other time was a negative 1.5. And as we know, you can't have a negative time. So we're going to cross that one off the list. But I am now going to take this time, and I'm going to throw it into my average velocity equation to figure out where is it actually going to land. 17.77 meters. So that's the exact location it lands away from the end line. So there's a whole bunch of ways of approaching this. There's tons of ways of solving this, and it's really up to you to try and figure out what's the best way for the given problem. So as we always like to say, have fun.